if the radioactive decay occurs, then the cat will be killed, but because the poison will be released in the box. And if the radioactive decay does not occur, the cat is not killed. The cat is alive. Now, if it's in a box, nobody's observing it. So when somebody opens the box, they have a probability. The cat.
Okay, I don't hear anything right now.
Do you find anything when you speak on it?
Yeah, I unmuted it.
Anne, can we shut those up? Okay, I mean, there are technical problems that we don't have to hear.
It's probably just over there.
Okay, so if you're the person who's responsible for this box, if you wait the half-life of the nucleus, then the probability is half that the cat is dead and half that the cat is alive. And you can't tell which until you open the box, according to quantum mechanics. And Schrodinger said, what does the cat think of this? What does it mean to have a state of the world in which the cat is half alive and half dead? If the cat wasn't waiting for you to open the box, what was it doing in the meantime? Right? The modern answer to this paradox or this disturbing experiment is that cat states are unrealistic in the sense that if you what's called a superposition, an equal probability situation for cat alive and cat dead, where both coexist, awaiting someone to measure it, is unrealistic because the world is always doing measurements. The air molecules inside the box, which are necessary if the cat is even going to have a chance of being alive, those air molecules will be able to tell if the cat is alive or dead. If the cat is dead, they'll be lying still on the floor, and the air molecules will know a big difference between a live cat and a dead cat, and so forth. So the world is doing lots of observations on any large object, and so it doesn't. So the fate of the cat does not. The cat's fate does not await the physicist opening the box to measure, because the world has measured before. If you had a completely evacuate, well, it doesn't work for cats, obviously. If you had, but actually nowadays we don't have Schrodinger cats, but in the laboratory we do have, I would say, Schrodinger kittens, small objects that are completely isolated, but not terribly small. They're getting bigger and bigger as physics advances with time and quantum technology gets bigger. And a quantum computer will be a kind of Schrodinger cat. It'll be a superposition. It'll have a different states with non-zero probability. And we try to keep the outside world from making measurements on it. That's the big challenge. How do we get cat-like states or kitten-like states that explore the whole possibilities of quantum mechanics? How do we shield them from the outside, from the world making observations and taking the results into probabilities instead of mixture, so-called superposition, where all the possibilities are still present. Okay, we can put this to positive use, and I won't go through the elaborate details of these protocols, but an important use potentially of this sensitivity of entanglement and quantum information to observation is to detect when somebody has made an observation. So if you want to have secure communication between two people, and in this game, they're always called Alice and Bob. So if Alice and Bob want to share information securely and be aware if anyone interfered, has eavesdropped on their communication. One way they can do it is use entangled pairs of photons, and anyone who makes an observation to tell what the state of one photon is will foul up the probability of the other. So you can exploit this sensitivity or delicacy of the results, that measuring one affects what you can measure about the other, to encrypt information. Now, I've talked about pairs of photons. We could, of course, have more than pairs. We could have large numbers of photons or other qubits, electron spins, or many other things have been discussed. And then it's really complicated, because you can measure in one direction or 45 degrees or other directions, and you can measure independently. You can make an independent choice on every one of your qubits. So there's a lot of information to keep track of. You have to have a definite probability for every possible measurement that can be made. The objects that do the bookkeeping of that, according to the principles of quantum mechanics, are things called wave functions, or more generally density matrices. But let me I'll show you what both of them look like in a simple case of 3 qubits. So this is going to be the only equation in this lecture. The wave function for 3 qubits, remember the qubits can either be 0 or 1. So in the case of polarized light, we'd have 0 would be vertical and 1 would be horizontal, or vice versa, say. And in general, when we have 3 different photons in a complicated state, any possible result can emerge. Okay, in special cases, they might all be vertically polarized. Then A0 would be 1 and all the others would be 0. But in general, all the possibilities would be represented. For instance, if we had 3 photons, all of whose polarizations were diagonal, then if we represented them in terms of the vertical and horizontal components, everything would, all the coefficients would be not 0. And you might want to entertain yourself by figuring out what the coefficient should be in cases like that. I'll give you the answer. They should all be equal. And if you want to be careful, you have some plus signs and some minus signs. In any case, in general, therefore, to represent the state of 3 qubits, you need numbers in front of all the possibilities. And in the formalism of quantum mechanics, the squares, these are called amplitudes in the wave function, and it's the squares of, and those are complex numbers in general, and it's the square of the magnitude of the complex number that tells you the probability of getting that particular result. Okay, so, and this is referred to the polarizations in horizontal and vertical directions, out of which you can build all the other polarizations by taking sums and differences and combinations with phases, you know, to get diagonal polarization or circular polarizations, as we showed last time. But the vertical and horizontal polarizations are enough if you allow yourself to add the possibilities to reconstruct an arbitrary direction, and including elliptical and circular polarization. Okay, and I won't, maybe if students are interested in, I'll talk about why you need density matrices in general, but for so we want to move on, we'll just leave it at that for wave functions. So now I want to segue into a discussion of topology in physics, which might seem to be totally disconnected, but you'll see that there's a beautiful, beautiful connection at the frontiers of physics between these quantum entanglements and entanglements in the sense of topology. So I'll talk a bit about the history of topology in physics. It really came into its own in the 19th century when people started studying little cyclones, or what they're called vortices, inside fluids. So tornadoes, if you like. And a beautiful example of this is smoke rings. And I don't know if you've ever played with smoke rings. You can, well, not so many people smoke anymore, and that's a good thing. But when people did, it was possible to blow smoke rings and just puff, and out would come these rings that keep going, that would persist. And if you do two of them, they can pass through each other, and they have remarkable properties. This in the 19th century, people were so struck by this that they constructed machines that created big smoke rings. And there's an elaborate theory in hydrodynamics of the properties of smoke of these vortices. So when you have a closed smoke ring, you have the particles moving around in circles and closing. So it's like a cyclone that closes on itself to make not a funnel, but a closed ring. And that vortex has a kind of persistence and stability. So these are, and they have a kind of topology in two senses. First of all, they have topology in the sense that they're rings, so they have a hole in them. But also the circulation pattern is, if you think about it, you have directions of velocity which go all around a circle once, and that's a topological property. It winds, the direction of velocity winds around the eye of the vortex exactly once, and that's the key to its stability. So you have winding around once within the vortex, the velocity of the smokes in the vortex, and then you have the whole thing closing up into a circle or an annulus. So topological properties, like how many holes something has, or how many times an angle winds around a circle as you move around, those are typically discrete. When you have winding, it's a number. You wind around a number of times, and you could also have negative winding if the direction is the opposite as you move around. But it's a whole number. If you have things that have holes in them, there's a whole number. And in general, topological properties are discrete, and things that are discrete also tend to be distinctive, because there's a significant difference between 1 and 2 that you can't fudge, and persistent, because small changes, small perturbations can't change 1 into 2. To change 1 into 2, to change a topological quantity, you can't change it a little bit. You have to change it a lot or not at all. So these properties, that you have things that are discrete, persistent, and distinctive, are very reminiscent of atoms. Atoms come in a few kinds, the periodic table of elements. They're persistent, they have a lot of stability, and they're distinctive. They have distinctive properties, each one, that depend, that are reproducible. And so this suggested, especially to a very imaginative and famous physicist, Lord Kelvin, in the 19th century, that atoms, people didn't know what atoms were at that time. Many people doubted that even there were atoms, but Kelvin was one of the enlightened people who believed in atoms, and he thought that it was a very intriguing possibility that atoms were vortices or knots in the ether. So the ether, which was the thing that was supposed to support electromagnetic waves and light, that fills all space, could get messed up and have vortices within it. It was kind of a material, and those would be the atoms. Beautiful, beautiful idea. Totally wrong, but a beautiful idea. And very stimulating to people. It stimulated in particular his friend John Tate to a careful mathematical study of knots that founded the modern subject of knot theory. And so here's what Lord Kelvin said: it's a dream unproven, it can prove nothing, and speculations founded upon it are dreams about dreams. I think, though, he really believed in it. He just didn't want to be associated with speculations. So a CAY there. Okay, anyway, that was the theory, and it's wrong as a theory of atoms as usually understood in chemistry and material science. However, its spirit lives on. Because there are many situations in the physical world in which you do have topological objects. Smoke rings were one, of course, but also macromolecules that can be long and linear can get knotted up. DNA gets knotted up inside our chromosomes, very much so. You have to compact the DNA molecule that, if you stretched it out, would be 6 feet long into a few microns. So it gets all balled up, and yes, it does have plenty of knots in it. And that's a very interesting subject, how it gets unknotted so it can be copied and so forth. You can have defects in solids, sort of generalized cracks that have a topological character because the underlying lattice of atoms is disturbed in ways that are discrete, that you can classify. And you can have vortices in fluids, that general smoke rings. You can have vortices of magnetic field, so magnetic flux tubes where magnetic field lines like to bundle, and then these are what, if you've ever seen pictures of the chromosphere of the sun, you might see these lines penetrating out. Those are magnetic versions of vortices. So there are many, many realizations of the topology in physics, and it's when you can identify a topological property, it's especially interesting just because it has these properties of being distinctive, persistent, and discrete. Now I'm going to talk about using topology to do computation. So I said that these properties were reminiscent of atoms. They are also reminiscent of information, of digital information. You want information that's discrete so that you can correct errors. So there's a definite error, there's a definite answer that if it's off a little bit, you can correct it. So you can read it out. So the use of topology to facilitate information storage and communication goes back a long way. In fact, it was used as the system, it was exploited in a system of communication, especially in Mesoamerican and Inca civilizations, where there were isolated tribes on different mountains that often spoke different languages. You needed a universal means of communication that was nonverbal, that they could use to settle accounts or tell stories or things like. And they developed this method called quipu, which is putting knots on an overlying rope, like here. This is what it looks like. I'll show you a more fleshed out picture momentarily. And you can store numbers this way, but you can also store pictures, digital images, if you like, or concepts. And this was used for many centuries as a method of communication down there. And here's what actually you can also you can combine. By the way, you can combine to get more information. You can use strings of different color. Okay, so you might want to, like in a library, this yellow ones might be about science, and black ones might be about military formations, and purple ones might be about sales results and so forth. So, what about a quantum version of this method of storing and manipulating information? It might seem far-fetched, but actually this is exactly one of the most exciting frontiers of physics today, the possibility of making quantum computations using the proper topological properties of a new kind of particles called anyons. So these are QQ, quantum in the net, and generalizing qubits. This is QQ, but nobody uses that name. I just made it up. The name is anyons, which I also made up. But this is now quite respectable. So anyons are a new kind of quantum particle. To understand them in context, we have to first understand what's new about them, what makes them different. So let's do that little digression before we get back to anyons proper. So for a long time, back till from the beginnings of quantum mechanics, the modern version of quantum mechanics dates from 1924 or so. But even earlier than that, people distinguished two different kinds of particles. In the old quantum mechanics, it was less clear mathematically what they were, but there was still a classification into two types that are called bosons and fermions, after the physicists who introduced them. Bose was an Indian physicist, and Enrico Fermi. So bosons and fermions exhibit very different behavior when you bring several of them together. And this is worth expounding on a little bit more. Famously, quantum mechanics unifies the description of particles in different aspects. Particles sometimes behave as waves and sometimes behave as particles in the sense of units, famously. So there's a wave-particle duality. Sometimes people talk about wavicles. So light, usually in practice, is in many circumstances is appropriately described as a wave, an electromagnetic wave, but it can also take the form of photons if you do the right kind of experiment. You bring out its particle aspects. The correct thing is a wavicle. It's both. And similarly for electrons, we ordinarily treat them as particles, but they also can have wave behavior. You can have interference effects among electrons, for instance. So in fact, the two of them are described both of them by the more general unified concept of a wavicle that incorporates both particle and wave aspects in a mathematically consistent way. So beautiful. So now all kinds of matter are just described by one concept. But and most quantum mechanics books stop there, but actually when if you go to two particles, they're different again. They're bosons and fermions. And bosons formally like to occupy the same quantum state. So if the possible amount energy levels or available to this particle are depicted here, and so for physics students, this is harmonic oscillator. Well, if you have bosons, they're very happy to all occupy the lowest energy state. But if you have fermions, they refuse to occupy the same quantum mechanical state. This is called the Pauli exclusion principle, which is a basic property of fermions that Wolfgang Pauli elaborated even before modern quantum mechanics, and is a key to understanding the nature of atoms and their spectra, among other things. So I'm in the spirit of these lectures, I won't be talking technically about these things, but for our purposes, bosons want to do the same thing while fermions refuse to do the same thing. This is called quantum statistics. That's kind of a misleading term, because statistics calls to mind that you have large populations and sample them, and this is not that. Even two particles can have quantum statistics, and it's a different thing. But the name, it's too late to change the name. It's called quantum statistics. So examples of fermions are electrons, neutrons, and protons, some of the important building blocks of matter. And the fact that they're fermions is absolutely crucial to how they behave in the physical world. Without the property of Fermi statistics, when you have an atom and you have many electrons around the nucleus, the electrons would all want to be doing the same thing. And so you wouldn't build up chemistry. You wouldn't build up the characteristic behavior where you have closed shells, because you occupy all the states up to a certain energy. And then when you want to add one more electron, you have to start a new thing, and that gives you the periodic table. Also, looking inside the atom, when you have protons and neutrons, there's a similar story, that it's because they refuse to occupy the same state that nuclei become more complicated and build up. It was actually proved mathematically by Dyson and Lanford that if not for Fermi statistics, if you treated electrons as if they didn't have this property, just as if every electron was different from every other one, then matter wouldn't be stable. It would collapse. Okay, so we often talk about there being four forces of nature, four basic forces: gravity, electromagnetism, and the strong and weak forces. And that's correct in the sense that those are important properties that govern the equations of the behavior of the world. But there's another kind of force which is extremely powerful. It's not it's so basic that it's built into the structure of quantum mechanics. So it's not really thought of as a force, but really just as part of what it means to be a quantum mechanical object, either a boson or a fermion. But it acts like a force. It acts like a force of a force encouraging conformity in the sense of, in the case of bosons, and a force that is a kind of repulsive force when the electrons refuse to do the same thing because of the Fermi statistics. So a dramatic example of that, going from the micro world of atoms to the astrophysical world, is atoms are supported by Fermi statistics resisting the tendency of electrons to all want to go onto the nucleus electrically. Okay, electrically, all the electrons would like to collapse right onto the nucleus, which has a large positive charge. However, Fermi statistics says, no, no, you can't do that. And that's the origin of the periodic table. When you get to really large objects, white dwarf stars, where the stars have exhausted their nuclear fuel, so they get cold. And at the end, after they've done that, they start to contract because of gravity. And if the stars have a mass around the solar mass, after they've maybe thrown off some matter through their evolution, then the force of gravity can be successfully resisted by electrons, by the electrons inside. So you can, due to the Fermi statistics, and that's a kind of giant atom. And similarly, for slightly more massive stars, they collapse even further past the white dwarf stage, and they collapse into neutron stars. In this case, it's the Fermi statistics of the neutron that supports the object against gravity, and that's kind of like a giant atomic nucleus. So very beautiful thing that the Fermi statistics governs both the very small objects and the very large objects. So it's turning very briefly to bosons. The boson statistics is a force for conformity. And so this is what makes lasers possible. When you have photons, you have a lot of photons doing the same thing, then other photons want to do that too. And that's why in a laser beam, you have lots of photons, all of the same color. So all in the same quantum mechanical state, they have the same color. If you look inside, you'd see how they have the same spatial profile, the same polarization and so forth. And it's because the Bose statistics encourages them to do that, that lasers are possible. So now, what about anyons? Well, for many years, physicists believed that bosons and fermions were the only possibilities. But in the 1970s and early 80s, some of us realized that if we lived in a two-dimensional world, so we re-examined the proofs, the so-called proofs, that those were the only two possibilities, and found that those proofs work in a three-dimensional world. So that's a relief. In the 3 dimensions, it gives a profound understanding of why those are the only two possibilities. But if the world were two-dimensional, there would be lots of other possibilities. And I'll sort of show you why. But in any case, these emergent particles in 2 dimensions that have not bosons behavior and not fermion behavior are called anyons. There are lots of different possibilities for anyons, but the generic name for all of them is anyon. So anything that's not a boson or a fermion is called an anyon. So anyons have a kind of memory. I'll make this, I hope, very clear in a picture momentarily, but the verbal statement is that they, or more precisely their wave function, keeps track of how many times and in what pattern they've wound around each other. So they really are very much in the spirit of the quipu, where, however, it's not the physical objects that are entangled with each other, but rather their paths through space. So you have objects that live in a 2-dimensional environment, but if they move through time, I should say, so move in time, time is like a 3rd dimension. So if you plot the trajectories of their motion in 3 dimensions, you get what's called their world lines. And world lines can be knotted up. And it turns out that in suitable states of matter or engineered systems, you can arrange that the quantum mechanical wave function of a system of 2-dimensional objects, these anyons, depends on exactly how the world lines get mixed up. So speaking sort of metaphorically, but not metaphor. I mean, it's really true. You transfer the entanglement of the world lines. So the motion in 2 dimensions through time of several of these particles, they get knotted up. We say technically they braid, and that entanglement gets reflected or registered, if you like, directly in their wave functions. So braids can get very complicated, as you see here. That means that you can store a lot of information in entangling world lines. If you have a lot of world lines, you make a complicated braid. There are many, many possibilities, and you can use that as a kind of code to keep track of a lot of information. By the way, the fact that braids have topology is what makes it possible to do an elaborate hairstyle like this, tie it up with a rubber band at the end, and then go about your business through the day without fearing that it'll become unraveled, because the different braids are topologically distinct. You can change them a little bit without changing their the nature, cutting the hair, or they won't just slide past each other. Here's a more abstract picture, which will, at the moment, I'll just for the moment, just ignore these bits here, the words. We have a lot of particles that live in a 2-dimensional plane. As they move around in time, okay, they always have some position in the 2-dimensional plane. So if you imagine just keeping track as a function of time of their 2-dimensional position, they make these lines, they're world lines. And as you see, the world lines can get very complicated, and they make literally braids. Since braids can get very complicated, systems of anyons can remember a lot by getting tangled up. You can encode a lot of information in the structure of these braids. And you can do that systematically, just as you can go on the internet and read about ways of making elaborate braids. You can also do that to do computations and record information. Now, you might think the fly in the ointment of all this is that it's about particles in 2 dimensions. In 3 dimensions, it doesn't work, and that's basically why you can't have anyons in 3 dimensions, particles that have this kind of memory, because if you try to make a knot now in 4 dimensions, so 3 space and 1 time, try to do something similar for particles that move in 3 dimensions, 3 dimensions of space and 1 of time, that doesn't work, because knots in 4 dimensions can always be unknotted. They're not topologically different. Think about it. If you have 2 strands and you want to move one past the other to unknot it, if you have an extra dimension, so one of these directions is time, the other 2 are space. If you have an extra dimension of space, then you can use that to move this one into the extra dimension, one of the strands into the extra dimension a little bit, then pass it through. Since it's in a different place in the extra dimension, they don't really cross, and then bring them back. And so you can unknot anything in 4 dimensions. So in 4 dimensions, knot theory is trivial, or in 3 space and 1 time dimension, this possibility of entangling world lines doesn't exist. That's the ultimate reason why you have only bosons and fermions in 3 dimensions, but in 2 dimensions, you can have these entanglements, and that gives rise to a much richer menu of possibilities. Now, but okay, we don't live in 2 dimensions. What about that? Well, actually, we do, or we can. We can make things that are essentially 2-dimensional. So particles that move in a confining geometry, so a sandwich structure, say, or chips, where they move in 2 dimensions. And as long as in quantum mechanics, it may take a finite amount of energy to escape the well to get into the 3rd dimension. And as long as you don't have that much energy, it's a strictly 2-dimensional world. And then anyons are possible. And this was a wonderful possibility that revised the foundations of quantum mechanics sort of 60 years into its development. So when we talk about particles here, we're not talking about fundamental particles, but kind of emergent particles. What is a particle? A particle is a stable concentration of energy. Inside matter in different states, the stable concentrations of energies don't necessarily look like electrons or photons. They look like they're collective things and can have topological properties. They can be like little cyclones. And in fact, the anyons are often concentrations of a kind of magnetic field. So they're little magnetic flux tubes, which when you cut into 2 dimensions makes them just flux points. Okay, so that, but I'm not going to talk about how the details of how you realize this, which is in materials, which is a very interesting research subject, but quite advanced. Okay, anyway, I'm very proud of having predicted that in something called the fractional quantum Hall effect, you would have anyons. This was an exotic state of matter that people discovered in the early 1980s. It's been the source of several Nobel Prizes. And at the time, and I predicted that the quasi-particles would be anyons. And I thought that this prediction would be tested in a matter of months, but actually it was only in 2020 that it happened. And this was the preprint. The paper was later published, I believe, in Nature. So anyonic braiding statistics. And let me show you the concrete nature of this pioneering experiment. So you can see the dimensions here is is microscopic, 200 nanometer, or not super microscopic, but sort of mesoscopic, we would say. And what you have here is an exotic state of matter called the fractional quantum Hall effect, which is the thing that's supposed to have the anyonic quasi-particles. And what you do is run currents so that they can follow either of 2 different paths. So inside this state of matter, currents only flow in one direction. So they're always flowing clockwise in this picture. And there are 2 ways of getting from here to here. If the possibility of jumping from one side to the other is rare. So the 2 ways you can get across in one jump are either jump here or jump over here. And if you think about it, if the particles that are moving around here are anyons, and you also have anyons in the middle, then depending on whether you go around this way over the top and come back here, or the more direct way over here, you either have or haven't wound around the world line of the particle in the middle. The particle in the middle just has a straight world line, it's not moving, but the particle involved in the current can either go around this way or that way. And the difference between those 2, if you imagine going this way and then back the other way, is a winding around. Okay. So the contribution of these 2 currents to the total current, these two subcurrents to the total current, depends on how many anyons are in the middle. So this particle on the outside registers information about how many anyons are in the middle, theoretically. Okay, and now we could predict exactly what the effect was supposed to be. And this beautiful experiment, which measures the records the current as a function of how much magnetic field is applied, shows these characteristic jumps. So there's discrete jumps, and the interpretation here is that as you change the conditions by changing the amount of magnetic field to accommodate that magnetic flux, the quantum Hall state only allows magnetic flux through in vortex points. And so you have jumps whenever an extra enyon appears in this central island, and you can predict the exact nature of those jumps, both their magnitude and where they occur, based on the underlying quantum mechanical theory. So this was the experimental demonstration of the existence of these theoretically predicted particles. Finally. Now, that's kind of seems esoteric, and it is esoteric. Okay, it's a very peculiar observation. You put things and you make things very cold, you use very pure materials, you put them in a magnetic field, vary the magnetic field a little bit, and you see this little blip in the current. However, let me remind you that in the early days, transistors were also a very esoteric technology, and they were things that were the size of your fist and were very delicate to make. But the ideas were things that you could scale down and engineer and make more powerful. And Microsoft now, which actually sponsored that experiment in part, it's part of a big initiative to use anyons on an industrial scale and their braiding to do computing, to use this property that I alluded to, that braids can get very complicated and store information, and by making braids in intelligent ways, you can do computations in the style of QPU. So let's go back to this picture and see how that works. You create a bunch of anyons, say by fiddling with magnetic fields, the way I showed you, and then you move them around, which you can also do with magnetic fields or electric fields. You in the experiment, they were moved around by having voltage so that the current flowed. So that's electric fields. You can move them around in controlled ways to make elaborate braids. The great advantage, and then you can read out their wave function by making observations analogous to measuring polarizations of photons at the end. That's how you can get information about what that precious wave function that has a lot of information in it is. The great advantage of doing things this way is that, as I mentioned, in general, quantum correlations, entanglement is very delicate. The world is out there making observations and may not make the observations that you want to get the information that's of interest. We want to make Schrodinger kittens that keep their secrets until we read them out, and keep track of what's happened to them, so they have life histories that are interesting, and we don't want them to die along the way. The great advantage of this way of encoding quantum information is that it's topological. So if you have the external world making observations, as long as those observations aren't too violent, they don't foul it up because they don't change the topology. So again, the great thing about topology is you have to change it a lot to change it at all. And here, that is addressing the main challenge of quantum computing, which is the delicacy of the entanglement, the information that's encoded through entanglement. Well, in view of the time, I won't say much about this, but earlier experiments have shown ways of doing similar things on a small scale in an engineered system. So the engineering is already underway. Many other interesting states of matter and engineered systems are predicted to contain various kinds of anyons. Now we know that this third family of possibilities beyond bosons and fermions, and they have this especially interesting property of having a memory of where they've been. Theory got way ahead of experiment, as I mentioned. It was the basic concept is almost 40 years old now. But experiment is now rapidly catching up and in new directions, going way beyond what was thought of in the early days. So I think it's a safe prediction that physicists will be exploring these anyonic worlds for years to come. So if you're a student, it's a good time to join the party. And so in conclusion, grades are beautiful. Thank you. And we'll adjourn the class to upstairs, 462, and we can have a discussion of this or any other matter that arises.